All right, very good. So last time we stopped at the point where we want to build a heap for this list of numbers. Okay. And of course, for this list of the number, if we simply add the numbers into an array, then we will have a tree like this, right? So let's say we have 2 and then 4, 1. So we just fill out the tree, or in other words, fill out the array from left to right. Okay, and then we have a tree like this, and we know that this one is a binary tree, but it's not a heap, right? Remember that a heap is a binary tree that satisfies two conditions. Number one, the shape condition. So it satisfies the shape condition because it's a complete binary tree, meaning it's full until the level before the last, and for the last is full from left to right. Okay, so it satisfies the shape condition, but it does not satisfy the order condition, meaning the value here at this node is smaller the value of left child, and so it violates the order condition. Remember that for being a heap, the value at any node will have to be bigger than the value of the left child and the right child, right? So for every node, so that's it. For an arbitrary sequence of numbers, uh, it does not satisfy the condition for being a heap. If we simply consider this sequence as an array, meaning we just keep adding the numbers into the array. So we will try to design an algorithm for helping us to build a heap for an arbitrary sequence of numbers. Now, as usual, we can consider this one as an array. We will do that exactly in the same manner like we fill out the tree. So we have 2, 4, 1, 9, 14, 16, 10, 7, 8, and 3. So keep in mind that when we work with the heaps, we are working with the array. Yeah. And I use the tree here as an illustration so we can see the ideas better. But in other words, starting from here, if we look at this node, then we can know what is the left child, what is the right child, right? By using the formula I reminded you last time, right? And we can also know what is the parent of 9, right? 4 divided by 2 is 2, that is number 4, okay? So now we will try to design an algorithm for building a heap. And the algorithm is very simple. We simply look at the sequence and we go from left to right. Similarly, we can look at the tree to see how it works first, right? So the idea is as follows. Starting from the first node is a heap, right? Because any tree with one node is a heap. So now we will try to consider the next subtree that has one more element, meaning here we have 2 and 4. So we consider this subtree by adding one element at a time. Okay. So when we look at this node, we will try to compare with the parent. And if it's bigger than the parent, then we know that the order condition has been violated. So we will try to correct that by swapping the value, right? So that's it. We will have 2 here and 4 up there. swap them. We have 4 here and we have 2 here. So next thing, we will try to consider a bigger subtree that has one more node. So in other words, we will try to consider this subtree. Okay, so this subtree, now we are looking at the new node. This one is smaller than the parent, so we are done for this subtree. Yeah. Now we add one more element. Now we consider the current node that we just added, compare with the parent, and if it's bigger than the parent, then we swap 2 here and 9 up there. Okay, we swap. But now, after we swap, we still have to continue because the chances that 9 here is bigger than the parent, right? So that's it. We start from here, we go, yeah. If it's bigger, we swap, and then we continue the process until the root of the tree. So meaning bigger than 4, so we swap, right? Okay, and we just have to do it for the newly added node. Yeah? We don't have to worry about the other branches because we know that the other branches have been satisfied with the shape condition and the order condition, right? So now, continuously, we can do it here on this one more node, right? Okay, so that's it. Compare. If it's bigger, swap, and then continue until we reach the root level. So meaning swap again, okay? So that is the idea. How can we translate the idea of working on this tree with the actual data structure we use for our algorithm? Namely, we have here an array. So what we will do is that, similarly here, right? We start from the next node because the subarray with one element here is already a heap. Okay? So we will try to build a heap by considering node by node until we reach the end. Okay? So from here, 4 is bigger than 2, so we swap, right? Okay. Now we move to the next node. Okay. 3, we compare with the parent. We know that the parent of this is 1, right? 3 divided by 2 is 1. So we compare with the parent is smaller. So we don't do anything. We move to the next. So now from here, we compare with the parent, which is 2, right? So we swap. And now after we swap, we have to continue because this position is not the root yet. So we have to compare with its parent, which is 4. And because it's bigger, so we swap. So we have 9, 4, right? Okay, so that is the idea of the algorithm here for building a heap. So that's it. Starting from the first array that has one element, we keep adding the new elements in and then try to rearrange the array or rearrange the tree. Okay? And finally, we will have a heap. So here is the algorithm that represents the idea I just presented. By the way, before we come up with the design for the algorithm, let me ask you to finish the work here by yourself. So tell me what kind of hit or what kind of results you have after we add one element at a time and try to rearrange the node. Is what we call reheap up, because once we add an element, we try to reheap by going up until we reach the root level. Okay? That is what we call reheap up algorithm. So continue to work and tell me what you have. So I'll give you, let's say, 3 minutes. And then after you finish, type in a list of numbers on the message so I know what results you have. Okay, so what do you have? Just type in a list of numbers that will give us a heap from this input. Okay, Caleb, you have 16, 9, 14, 8, 4, 1, 10, 2, 7, 3. Very good. Yeah, that's it. All right. Okay, so you got it. All right. So anybody else? You have the same results or a little bit different? All right, very good. So if you have the same result, that is the correct one. All right, so let me show you the algorithm. So the algorithm is very simple, right? So given an array of numbers as the input, we just have to have a for loop, okay? For I from 2 to n, right? Then just reheap up from that I position, right? So it's very simple, and reheap up involving finding the parent, compare, and if the new added value is smaller, that is fine. If it's bigger, we swap, right? And if the parent is greater than 1, meaning the parent is not the root, we have to continue, right? So that is the idea. So let me show you the algorithm. Okay, so that said, we have for I from 2 to n, see, it should be to n, okay, because normally we talk about the index from 1 to n, right? So we start to reheap up. So reheap up means that we find the parent. So this one should be n. Yeah. And then we just find the parent, and if the value we just added is greater than the value of the parent, then we swap and then reheap up for the parent if the parent is not the root yet. Okay, so that is what we have. Okay, so for some reasons it does not shift this. Okay, so this one should be, okay, when the if condition is correct. So for some reasons why I exported to PDF, shift the two statement. Yeah, so the two statements here should be inside the if AI is greater than AP. I will double check that. We should not have that problem on Moodle, because on Moodle I use PowerPoint. Okay. All right. So that is the algorithm. Okay. Now, what I want you to do is that I want you to use the techniques you have learned about analyzing the algorithms for finding what is the complexity for building a heap. Yeah, so how much does it cost for building a heap of size n? So if you have n elements, then what is the complexity? So, all right, for this case, take it as an exercise. But when we analyze this one thing you may need is that we want to know what is the height of the tree. The height of the tree. Okay. So here, a heap is a binary tree that is complete, meaning it's full until the level before the last, and on the last level is full from left to right. So what is the height of this tree? So I will work out the calculation for the height. And once you know the height, then you can analyze the reheap up, and then the build algorithm I'm showing on the shared document for you. Okay, so first we analyze the height. Now, here we have one example, and in general, if the tree has n elements, then what is the height? Yeah. So here you have, if the height is h, which is a number that we have to find. Okay, let me cancel this presentation. Yeah. So if the height is h, right? So that said, we have the level 0 has one element, meaning we have 2 part of the 0. The second one, we have 2 more. Okay, the next one, we have 2 square, right? And then how about the last one? Okay. So if you have n elements, right, it means that it will continue. Okay. So remember that a heap is a binary tree that is full until the height, the level before the last. If the height is h, right? So it will go from what? Level 0, level 1 to, say, level h, right? Because the height is h, right? Okay. Then the one before the last will have 2 whole power to the h minus 1, right? How about the last level or the last row? The last row can have anywhere between 1, when we have just only one node on the last level, and then when it's full, right? When it's full, how many elements it has? 2 power to the h if it's full, right? So that said, if n is the number of nodes on the tree, right, then n will be less than or equal the full tree, meaning every levels are full. When do we have that? 2 power to the I for I from 0 to h. Okay? So it's the extreme situation when you have the full nodes at the last level. And n here will be bigger or equal the case when you have just only one node on the last level, right? So that is the situation for the minimum number of nodes on the last level. Okay, so that is sum of 2 power to the I for I from 0 to h minus 1 plus with one node on the last level, right? So n will be bigger or equal the sum of every nodes that involve the level before the last, right? And the smallest case is one when we have one node on the last level, and the biggest case is when the last level is full, meaning full 2 power to the h, right? So from here, we already know the sum, right? So this one is 2 power to the h plus 1 minus 1 divided by 2 minus 1 is 1, right? This sum is equal to this. And then this one, you have here 2 power to the h minus 1, right? Divided by 2 minus 1, which is 1 plus 1. This one is cancelled. So here you have 2 power to the h is less than or equal n, right? And then this one means that h is less than or equal log 2 of n. Okay. On the other side, you have n bring minus 1 to the other side, you have n plus 1 is lesser than or equal to power to the h plus 1. N plus 1 is greater than n. So here you have n is lesser than here, meaning n is lesser than, take log both sides, right? So take log both sides, you have here log 2 of n. Let me throw this one away. Okay. Here you have log 2 of n lesser than, take log both sides, h plus 1. So in other words, okay, h is smaller than log 2 of n, and then h is bigger than log 2 of n, okay, minus 1, right? Or in other words, what is h? Here is, okay, h. Here is h plus 1. Then log 2 of n is between, right? So in other words, the height here of the tree will be the floor of log 2 of n. The height is the floor of log 2 of n. But in general, we can just say that the height is log 2 of n because the difference is just only 1 unit, right? So that is what we have for the height. The key point here is that for a heap, the last row will have between 1 for the smallest number of nodes, and then the full, meaning 2 power to the h, where h is the height, right? H is the height. Then you have 2 power to the h. So that is the height of this tree, or the height of a heap. Okay, so once we know the height is log 2 of n, then you can analyze the complexity of the build and the reheap up algorithm. So that is one idea. Okay, one idea, meaning that whenever we add a new element in, we try to reheap up. Now, the reheap up algorithm I just showed you and asked you to analyze the complexity. What I can tell you right away is that the complexity of the build algorithm is big O n log n. Okay. So is it a good algorithm? Can we do a better job for building a heap? Yes, so the answer is that the reheap up algorithm we just learned is not the best algorithm for building a heap. We can do a better way, and it costs much less. Okay, so how can we do that? So here is the idea. So here's the idea, and you will see that we can simply change the idea a little bit, then we have a much better algorithm. Okay, let me clear this. Okay, let me start with the same example here. We have 2, 4, 1, 9, 14, 16, 10, 7, 8, and 3. Okay. So this one is the list of input numbers. Now, instead of reheaping up, what I will do is that I will try to go down, okay, instead of going up. So how does it mean? So I can start from, instead from the leftmost number, right, to the right, but now I will start from the rightmost number and work left. And you see, the idea is very simple, right? We just change the way we rearrange the numbers a little bit. Instead of left to right, now we work right to left. We start from here, okay? What I will do is that I will compare with the left child and right child and try to go down. But this one is a note that is at the leaf level, so it has no left child or right child, so I can skip them. Okay? I can skip this, 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 and now I come to this note. So I can skip all of the notes that is at the leaf level, meaning it has no left child, no right child, right? Or no children at all. So from here, what I will do is that I compare with the left child is bigger. So this subtree is a heap. So I don't need to do anything, right? So I will go to the next one. So I work from right to left. So next one, right? I will try to find out which one is the biggest value. So this one is bigger than the left and the right child. So it's in the good shape. So it's in the good order. So I don't need to do anything. Yeah. So the next one will be this node, right? Now, this one, I will find out which value is the biggest. The left child is the biggest, right? So I will swap with the left child. Yeah. So when I swap with the left child, now this one is the leaf. It's a leaf, so I don't have to do anything. Okay, if it's not a leaf, then I have to continue going down. Okay, so I think one of the examples will allow us to go down, but for this case, we don't have to do that. Okay, swap, and then we are done. Right. So now we go to the next. Okay, compare. The big value is here. Okay, so we swap. So we have 4 and 14. Now, this one is not a leaf, so we have to compare to see whether or not it satisfies the shape. I mean, the shape condition is true, but now we have to check if it's also satisfy the other condition. It's true, so we don't have to do anything, right? Okay. So after that, we go to the last one. Okay. So here we compare and we see that, okay, 16 is the biggest child. So we swap. So here we have 16. And now we have 2. Right? After we swap, 2 is not a leaf. So we have to continue by comparing with the children and swap with the bigger one. So we have here 10 and 2. Okay, and we are done. Okay, let's check to see if it's a heap. Is it? Yes, it's a heap, right? Okay. And is it different with what we got before? Yeah, it's different, right? But it's still a heap. So in other words, for an input, we may have different output as far as the output is a heap. That is fine, right? In fact, we can prove the correctness of the Biot algorithm I just shared with you, and also this algorithm as well. Yeah. So the correctness can be proved by using induction. Okay. If you can, try to prove it by yourself to see if the Biot algorithm is correct. Okay. We do that by induction. All right. So for example, previously, when we add a new element in, we will show that if, I mean, the base case is when we have one element, fine, right? And if we have the algorithm is correct after k element, okay, and now we have to prove that it's correct for k plus 1. Okay. We already have a heap after k steps. If we add one more, right, then whether or not the final result is also a heap. That is what we have to do. So here we can go what? Reheap up, still have a heap, or reheap down here. Reheap down is a little bit different. Okay? We have to use a little bit different induction than the reheap up shown here. Okay? So you can try to find out how can you prove the correctness of the here. We call reheap down, or sometimes we call it hippify. Okay. All right. Let me show you the algorithm first, and then we will try to talk about how we can prove that the algorithm is correct. Okay, so remember that, let me share the screen first. Okay, remember that here we have the reheap up algorithm and the Biot algorithm, in that we use the reheap up. So now the reheap down or hippify is here. So find out what is the left child, the right child, right? And find out what is the largest value. So if the largest value is a child, either left child or right child, then we swap, and then we continue to hippify or reheap down, right, until we reach the leaf level. Okay. All right. So now the example, you can try with the example I just showed you again, or I have another example on the screen. You can try it at home if you like. Okay. So we want to know whether or not the algorithm is correct. Let me skip all of this. And we will try to find out what is the running time. Okay. So here is the algorithm. Okay, so where did I have it? All right. So here is the algorithm. Build a heap. Hippify I just showed you before, right? So now we find out what is the size of the heap. And then we just have to go from half of that. Why? Okay. Let's say here we have the original tree, right? So we don't have to start from here, from here, from here, from here, because they are all node that has no children, right? So we just start from the one that has at least one children, right? So that is 4. And where is the index of this one? Is n divided by 2. And of course, we take the integer division, right? Okay, why n divided by 2? Because from this one, if the index of this is I, right? Then what is the left child? What is the right child? 2i, 2i plus 1, right? Okay, so if this one is n, then it has a child, right? So same thing, if this one is n. So that said, if n divides by 2, then we have the I, right? I is n divided by 2. That's why we can skip most of the index. So we just start from n divided by 2 using integer division, right? And then we go hippify. Hippify, as I showed you before, we have comparing with the left child and the right child, swap with the biggest one, and go down until we reach the leaf level. Okay? Now, is the algorithm correct? So here we have this. Assume that the algorithm is correct when we have k plus 1 element and k elements, right? Now we have to show that the algorithm is also correct for k plus 1 elements. How can we show that? How can we show that the new Bill heap algorithm in that we choose heapify or heap down is correct? Here is about breaking the big input into the smaller one, right? Remember that here we have k plus 1 elements. Then how can we use the assumption that the algorithm is correct for the first k element? Now we prove that it's also correct for k plus 1 elements. The reheap up algorithm was easy for us to prove that the algorithm is correct because we start from the leftmost, right, adding one by one. So if we have k plus 1 elements, we can assume that the first k elements have been added and we have the heap correctly. Now we add the last one. Okay? We add the last one by comparing with the parent, okay, swap and then go up until we have the root. Okay? That's easy if we prove it this way, right? But for this, how can we know that is the algorithm is correct? We cannot simply break the list here into k with the first k elements and the last one has 1, right? Why? Because the algorithm starts from the right to the left, right? Okay, so that means that if we have one more elements, how do we use the fact that the algorithm, when we apply for the first k element, is correct? Okay. So if we apply it for the k elements, we go from right to left here, okay, changing that. Now, when we have the last one, we have to read down, right? So again, we have to go back. Yeah. So that said, it's not easy by breaking the tree like this. So how? Okay, maybe I'll ask you to think about that a little bit, right? Use induction to prove that the algorithm for building a heap in that we use the heapify or a heap down is correct. Okay? So the idea is we have to use induction, but how? Okay? How to break? So in this situation, we may have to use not the weak induction like the previous algorithm, but we use the strong induction. Okay, so assume that the algorithm is correct for all input with length less than or equal k. And now we prove that it's correct for k plus 1. Okay, so that is a little bit different. Think about that, and next time we will discuss the solution for, let's say, how to prove that. Now, the next thing we have is how to analyze the complexity of this algorithm. Okay, so let me write it down here. So we will try to find what is the complexity of this build algorithm. Okay. So you will see that when we analyze the complexity of an algorithm, we have to pay attention. Okay? Sometimes a simple solution or the simple way to analyze the complexity may not give us a correct result. So let's say here we have the build heap. And array A, and right? Just change the algorithm a little bit so I can save some space here. So for I from n divided by 2 to 1. Okay, and we can have down to 1. Then we have heapify or a heap down. A, right? Starting from I. Okay, so the algorithm is pretty simple. And now for the heapify involve, let me have that one here. 18, let's see what we have. Okay, heapify here. So we have to compare, for example, starting from here, okay, compare with the left child and right child, right? And if it's smaller, then we have to swap and go down until we reach the leaf level, right? So that said, at any level, okay, how many steps does the Hippify cost? Let's say if I is the index of the node at the last level, or here when it doesn't have a child, then how many steps does it cost for Hippify? And this one, so basically we don't have to Hippify, right? Because we start from the one that has one, at least one child, right? So that said, from here, it costs 0 steps because basically we don't have to Hippify. From here, how many steps? Compare with the children, right? Swap and continue. So compare, take 1, 2 comparison, right? And the last one is to see if it's bigger than or smaller than the biggest child. If it's the case, swap, otherwise don't do anything, right? So basically you have, okay, here, a constant number of steps, finding the left child and the right child index, right? And then if here, okay, we have 2 conditions to check, right? And then again, we have another if, so it's 4 conditions to check, right? And then the last one here, so we have 5 conditions to check, right? And then if the case, then we swap, take 1 step, and then Hippify again. So depending on the level, okay, the level here, remember that here we have level 0, okay, level 0, level 1, level 2, until level the height of the tree, right? So now, for this level, it will take 1 step, big of 1 step, right? Because as I mentioned before, 5 conditions to check and then a swap, right? Okay. And then a Hippify, if this one, we have only bigger 1 step. For this level, we have 1, 2, right? So it's a little bit in the reverse order, meaning the level is smaller than the number of steps we have to go down is bigger. So that's why instead of considering the level, we consider the height. So this one we have the height 0. Okay. This one we have the height 1. This one we have the height 2. This one we have the height 3. So basically what we have, the level, okay, plus the height is always what? The height of the tree, right? Minus 1. So 0 plus 3. But here we have 0, 1, 2, 3. Actually, they are the same, right? 0 plus 3 is the height. Yeah, it's the height of the tree. So here we have level 1, and it has the height 0, 1, 2. So it's 3. This one, 2, 1 is 3 also. So basically, the height is just the reverse number of the level. But here, when we choose the height, it's easier for us to see if the nodes at the height, say 0, then we don't have to Hippify. Okay? The height 1, we have to do at most 1. the height 2, we have to do at most 2, right? So it's easier for us to see how many steps we have to walk down. So now, here you have n½ to 1 and hippify of every node. Okay, how many steps or operation we have to do? Okay, n½ time, right? n½ time for I from n½ to 1, n½ time. And what is the cost for hippify? This one, 0 step. This one, 1 step. This one, 2 step. And then the biggest height we have the height of the tree, which is log 2 of n, right? Okay, so let me stop the presentation. Okay, so a rough estimation of the cost for building the heap here, again, is n log n. Okay? But the analysis of this algorithm is not 100% correct. Why? Because here, when we have the index from n½ to 1, here you have 1 step, here you have 2 steps, and going up, the last node has log n step. Okay? It does not mean that for every node from n½ to 1, they are all take log n steps. The root, yes. The second level, log n minus 1, etc. But if we think that every node take log n, it's not very accurate, right? So here you have n½ nodes. Not all of them take log n. Yeah, the biggest number is log 2 of n, but it's just for the highest node, the second highest, the third highest, etc. So if we analyze it like this, by saying that here you have n½ cycle in the for loop, and inside that, each of the hippify cost, the biggest value is log 2 of n, then the complexity for build heap is n log n. It's not very, very correct, not very accurate, right? Okay, so we need to do a better job in analyzing the complexity of this algorithm. So how can we analyze the complexity of this algorithm accurately? We have to count level by level. How many steps does it cost when we hippify from that level down? Okay, so now let me add them and then see what we have. Okay, so now for the last one, you have 0 step, right? For the one before the last, we have 1 step. Okay. How many nodes we can have on the last level? So the level is 0 to level h, which is log 2 of n, right? So on the last one, actually log 2 of n minus 1, okay? Okay, because we go from 0. So the height is log 2 of n, so the last level is log 2 of n minus 1, right? It depends. I mean, if we want to go from log 2 of, I mean, from 0 to log 2 of n, that is fine. But the counting is a little bit more. So for a precise number, we can say that this one has log 2 of n minus 1 level, right? Because the total number on this is 2 power to the log 2 of n minus 1. This one is basically half of the number of the node. On the last row, the biggest number we can have is half of the total number of nodes. Okay, why? Because this one has 2 power to the log 2 of n minus 1. Okay. Now, all of the nodes on this level will have 0 step for the Hippify, right? So all of the nodes here will take no step for building the heap, right? Because no Hippify will be performed. Okay, remember that we go from n half, right? Now, the level before that, we have 2 power to the log 2 of n minus 2, right? Yeah, because every time we double the number, if we go this way, every time we have the number of nodes cut by half, right? So we have here 1 step, right? So the one before, we have 2 power log 2 of n minus 3, then we have, say, 2 steps, okay? So that said, if we add all of them together, then what is the summation we have? If we add 2 of them, right? And the summation, you can see that when you have the level is from 0 to log 2 of n, then yeah, this one will have what? Log 2 of n minus 2 steps, right? And then minus 3, minus 4, and then finally we have this one has 0 step. Okay, so that said, we can write down, keep in mind that you can match the number here and the number here. This one, minus 1, we have 0, minus 2, we have 1, right? So when you add them, you always have minus 1. Or in other words, this one will be 1 less than this one. Okay? Because as I mentioned before, the last row, we have 0 Hippify, right? The one before, we have half the number of nodes, and we have 1 more Hippify. Okay? So that said, the sum here will be using this 2, say, samples, we can write it like this. Let me write it down here, and then I will remove the one before. Okay, the sum will be sigma of 2 power to the log 2 of n minus I, okay, for I from what to what, and then time with the number of steps that we have to work down, right? So here you have log 2 of n minus I, okay. Okay, and then time with what? Remember that here you have minus 1, then we have 0, minus 2, we have 1, right? So here you have minus I, then what we have? one last, right? So we have I minus 1. Okay. When I from where to where? I here, you can see that we have from 1 to from 1, and then you have 2, 3, until we have 0. Okay. So that set is log 2 of n. Okay. Now, for I from 1 to log 2 of n, this one log 2 of n minus I, we can do the calculation, or we can simply use this one log 2 of n minus I. What is it? It's exactly log 2 of n here. Okay. So if you look at the level and the height are in the reverse order, right? So if log 2 of n minus I, look at this. This one is log 2 of n minus 1. Okay. When we add them, you have log 2 of n minus 1. This one you can have what? This one we can think about as the height. Okay, so that said, the height here can be log 2 of n minus I. What is the height? Simply look at this. Yeah. At the last one, if the level is log 2 of n minus 1, then the height is 0. Yeah, so we can replace this one by the height 0. Okay, so if you have, or in other words, log 2 of n minus I, what is the height? Okay. Yep. Very good. So you can replace this one by I minus 1, right? So the sum will be something like this. Sigma of I times 2 power to the I, right? So the formulas we learned before don't have that kind of formula. Remember, when we have the sum, okay, the geometric sum, sigma of 2 power the I for I from 0 to log 2 of n, or in general, we can have it at n, that is easier, okay, in general, right? This one is 2 power to the k plus 1 minus 1 divided by 2 minus 1, right? But here, if we have this one, the formula is a little bit different, right? Okay. Okay. Or after we transform this formula, we can have something like this. Okay. Okay. Sigma of 2 power to the I minus 1 times I. What is the sum? If we know how to find out the result for here, then we can know what is the result we have here. Because we replace this one by I minus 1, right? 2 power to the I minus 1 can be seen as 2 power to the I minus 2 times 2, right? So in other words, we can transform this formula back to this one. With here I minus 1. The reason why we transform this formula to this one, because we can easily find the result for this. Okay, so what is the sum here? Remember that I have sigma of 2 power to the I, for I from 0 to k is 2 power to the k plus 1 minus 1, right? Divided by 2 minus 1, which is 1. So we can remove this one, right? Okay. Now, we have this formula, which is the geometric summation. Okay. Now, if we take the derivative both sides, what will we have? Sum of derivative. The derivative of the sum is the sum of the derivative. What is it? It's the sum of I times 2 I minus 1 for I from 0 to k, right? If we take the derivative here, and if we take the derivative here, what is it? K plus 1 times 2 power to the k. Derivative of 1 is 0, right? So we know that here is the sum, here's the result. Okay? So the sum here is here, because we take the derivative here, take the derivative here. And so this one will be k plus 1 times 2 power to the k. Right? Okay, so that is what we have. All right. So now, what is the sum here we have? If we add every cos for the heap P5, meaning if k is log 2 of n, the height, all right, so time is almost over. So what I want you to do is that after we add all of them here, we have this formula, okay? Then we bring it to the easier form where we can find out what is the result, right? So now, from here, what do we have for the algorithm for doing here? Okay, so this one is a simple exercise. Time is almost over, so I will ask you to check it at home, and next time we will discuss about the final results. So keep in mind that we have two different ways for building a heap, one using the heap up and one using the heap down. And we want to know which one is better by considering what is the cost, right? The heap up, what is the cost? Okay, and then the heap down, what is the cost? So you see that two different algorithms with a little bit different idea can give us completely different complexity. Okay, all right, so check it at home by yourself before coming to the class next time. Yeah. All right, so I know you may have some questions, but that is what I want you to check at home, right? So next time I will answer all of the questions you can have when you analyze the complexity here. Okay, so that's it for today.